Good morning, students. We'll continue with our unit number 3, which is environment, and the topic number 3, which is hazardous waste management, flood control of dams, and multi-purpose projects, that is hydroelectric projects. So the first one is hazardous waste management. Hazardous waste management is defined as any solid is defined as any solid, liquid, or gaseous substance which, by reasons of any physical, chemical, reactive, toxic, or infectious characteristics, causes danger to health or environment when improperly treated, stored, transported, or disposed of, that is discharged. So, sources of hazardous waste includes industries, petroleum, refineries, transportation, coke ovens, blast furnaces, sludges, scrubbing sludges, and biological waste generating laboratories, thermal and nuclear power plants, and nuclear reactors, etc. So, the main objective of hazardous waste management plan is to eliminate or reduce the hazardous waste through processes of resource recovery. So, the waste must be accounted for from its origin to ultimate disposal. So, how the hazardous waste management cycle works is shown here in this picture. Public awareness is a must. Staff and equipment supply for hazardous waste management. Finance and cost recovery to manage the waste. Policy and planning of the same. Legal aspects and enforcement, stakeholder coordination, and capacity building and manpower training. Next, the major components of hazardous waste management plan are as follows. Number one, inventory, which I have already shown in the picture. This is the explanation. So all the industries producing more than 100 kg of hazardous waste per month should be registered. So an inventory of such waste generating agencies and the quantity of waste produced per month should be prepared. Number two, storage. The hazardous waste generating plants should equip themselves with special on-site tanks, chemically resistant containers or basins for storage of waste. Number three, transport. The waste must be transported by suitable tanker trucks, flatbed trucks or rail cars of the approved disposal sites. Number four, spillage. A well-publicized emergency plan should be prepared to deal with unexpected spillage or accidental release of contaminants during transportation to prevent environmental damage and public health hazard. Number five, disposal. The waste should be transported to a physical and chemical treatment plant for processing or concentration or hauled directly to an approved hazardous waste treatment facility for final disposal. Number six, waste exchange. When on-site recycling or recovery of waste is not feasible, that is not approachable, the possibility of waste exchange should be explored. So, transferring waste from large industries to smaller ones, which are able to reuse low purity oils, acids, alkali, solvents, or recover valuable metals and other materials from concentrated waste, can also be considered. The next topic is flood control of dams. So, flow through dams, also known as perforated dams, are constructed solely for the purpose of flood control and mitigation of flood risk in downstream communities and ecosystems. So, unlike reservoir dams, which are built primarily for water storage or power generation, the spillway, which is the opening, is built at the same height at the river level, allowing the river to continue its natural flow in normal conditions. When water level rises above the spillway, the dam restricts the amount flowing through the opening, decreasing peak flood flow. Since flow-through dams minimally affect rivers and natural flows, under normal conditions, negative environmental and socio-economic impacts such as sediment accumulation, restriction of water flow to downstream communities and ecosystems, and breaching during very extreme flood events can be minimized or avoided to get altogether. So flow-through dams are constructed in high flood risk areas, particularly those with important infrastructure and livelihoods. So planners, local decision makers, and construction engineers are the typical stakeholders involved in construction site choice as well as spillway and wall height selection and setting of desired river flow rates and dam carrying capacity. So post-dam construction, socio-economic and environmental impact assessment criteria should be established as part of implementation to avoid negative impacts on ecosystems and local communities. Operational management typically includes general maintenance and occasional clearing of sediments or other accumulations, preventing optimal water flow. So the next topic is multi-purpose water projects. The multi-purpose projects are explained here below. The first one is the Damodar Valley project. The aggressive Damodar during the rainy season, with all its surplus water used to engulf the entire region. So periodic and successive flood was so disastrous that Damodar was aptly known as Curse of Bengal. But after the construction of several dams, recurrence of flood is nowadays a bygone chapter. So storage dams were constructed at Tilaya, Maithan, Panchet and Konar. The combined area controlled by all these dams is about 13,500 square kilometers. Hydropower generation plants were erected at Panchet, Tilaya and Maithan. So three thermal stations were also created at Chandrapura, Durgapur and Bokaro to provide power to the core sectors of industry and commerce, example railways, steel plants, coal mines. The major objective of this pioneer maybe you should increase your volume because here the volume of my end it is full, and also those who are giving your attendance now, I won't accept it since the class is still going on and I am not asking for your attendance also now. So it would be better if you concentrate on the lecture. Okay. Okay, so number two, Bhakra Nangal project. It is the most ambitious project to convert large barren semi-arid tracts of northwest India into lush green fertile agricultural field. Bhakra Nangal project was one of the largest multipurpose Indian projects constructed over the river Satluj. So from the constructional point of view, indeed, erection of this dam was a remarkable achievement. So the entire work was undertaken jointly by the states of Punjab, Haryana, Rajasthan and central government. So after construction, Bhakra became one of the highest dam in the world. Broadly, the entire project is divided into two separate divisions. Check your network, Sanjay. The Bhakra Dam. So this project has the capacity to store more than 10,000 million meter cubes of water. So this lake is properly known as Govind Sagar. Number 2, the Nangal Dam. Constructed 13 km downstream of Bhakra. Any irregularities caused by Bhakra Dam is rectified here and it is the longest among all the dams and the stability of channel is maintained. So the combined length of Bhakra Nangal Canal exceeds 1000 kilometers. So apart from the two main dam storage, this project comprises of several other hydel projects at places of Ganguwal, Kotla with total installed capacity of over 1500 megawatts, number of irrigation canals like the Bhakra Canal, Nangal Canal, Bist Dope Canal, Nirvana Canal, etc. So nearly almost all of Punjab, large areas of Haryana and Rajasthan are benefited directly by the Bhakra Nangal purpose project. Next, the Hirakund project. Mahanadi is the lifeline of Orissa, so it enters Orissa from the highland of Naraj. So this rapid fall from considerable height is provoked by planners to erect this monumental dam at Hirakud. So this is the longest dam in India. The major benefits behind the construction of this dam were to harness the ample hydel power from swift flow of water to control of occasional flood and resultant havoc, irrigation canals to large areas of Puri and Cuttack districts, then improvement of water transport through greater navigability, overall economic development of the area by providing employment at the project, rapid industrialization of the area through the stable and assured power supply, and the increase of other minor economic activities like fishing and tourism. Number 4, the Nagarjun Sagar project. So this is the biggest river project in Andhra Pradesh. A dam was constructed near Nandikonda village. So this project was made to ensure irrigation water in Khamman, Guntur and Kurnool districts. The last one, number 5, the BS project. So this project was constructed as the extension of Bhakra Nangal project. The growing need of irrigation and consequent increasing demand of electricity compelled the planners to select BS as the potential source of water for another multi-purpose project. This project may be divided into two distinct parts. On one hand, canals were made to connect Beast River with the river Sutlej. Another high dam was created at Pong, which is at Himalaya. So, to meet the growing demand of electricity, particularly in the agricultural fields of Punjab and Haryana, hydel power plants were created at places like Dehar and Beast Dam at Pong. So this is a weekly assignment number 6. You have to explain how structures of flood control works, and also the second one you have to explain in the treatment and recovery of hazardous waste materials. The last date of submission is given here, and also from now on the last time of receiving the assignments is also given. It is till 12:30 p.m. of 23rd June. So you can give your attendance now in the chat box. The attendance that will be given now will only be considered. Those students who were giving attendance when the class was going on, I won't be accepting their attendance. I hope that's clear. Every class I used to tell it, but no one listens to it. So this time I am being more serious about it, so I won't be giving attendance to those students. Thank you.
Every year, floods make their way through populated areas, costing lives and millions of dollars in damages, devastating communities, and grinding local economies to a halt. If you've ever experienced one yourself, you know how powerless it feels to be up against Mother Nature. And if you haven't, be careful in thinking it can't happen to you. Nearly every major city across the world is susceptible to extreme rainfall and has areas that are vulnerable to flood risk. Luckily, we've developed strategies and structures over the years to reduce our vulnerability and mitigate our risk. We still can't change how much it rains, at least in the short term, but we found lots of ways to manage that water once it reaches the earth to limit the danger it poses to lives and property. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about how large-scale flood control structures work on rivers. This video is sponsored by CuriosityStream and Nebula. Get 26% off at the link in the description. More on that. We all know generally what a flood is. Too much water in one place at one time. But I think there's still uncertainty in how floods actually occur. Part of the reason for that confusion, I think, is the huge variety of scales we have when talking about flooding. Most river systems are dendritic. The topography of the land and long-term geologic processes mean that streams join and concentrate the further you move downstream, just like the branches of a tree. A watershed is the entire area of land where precipitation collects and drains into a common outlet. It's a funnel. And as you move downstream, those funnels start to combine. The further you go, the larger the watershed becomes as more and more streams contribute to drainage. So watersheds can be tiny or gigantic. Your front yard is a watershed to the gutter on the street. If it happens to be raining hard directly on your house, the gutter will flood, maybe even overtop the road onto the sidewalk. At the complete opposite end of the spectrum, more than 1 million square miles, or 3 million square kilometers, make up the drainage area of the Mississippi River in the US. A big rainstorm in one city is not going to make a dent in the total flow of this river. But if everywhere in the basin is having an unseasonably wet year, that can add up into major flooding as all that water concentrates into a single waterway. This seems simple, but it's a real conceptual challenge in understanding flooding, not to mention trying to control it. Smaller watersheds only flood during single intense storm events called flash floods. Usually this water is already long gone by the time the next storm comes. In contrast, large watersheds flood in response to widespread and sustained wet weather. They aren't really affected by single storm events. Of course, in a dendritic system, there's everything in between, which means a flood can be a local event affecting a few houses and streets for a couple of hours during an intense thunderstorm, or a months-long ordeal impacting huge swaths of land and multiple communities. Riverine flooding is also a challenge because it's not linear. This is a generalized cross-section through a river. You have the main channel where most normal flows occur. Every unit of rise in the river doesn't equal that much extra width in inundation. Plus, there's not much development within the banks of a river, maybe some low bridges and a few docks. But above the channel banks, things change. The slopes aren't so steep, and you end up with wide, flat areas of land. And you know what we humans like to do with wide, flat areas near waterways? We build stuff, like entire cities, that or use it as farmland. The problem is that once a channel overbanks, every unit of rise in the river equals much wider extents of inundation. You can see now why this is called the floodplain. And looking at a cross-sectional view, it's easy to see one of the most common structural solutions to flooding. Levees. If overtopping the banks of the river creates the problem, we can just make the banks of the river higher by building earthen embankments or concrete walls. Levees protect flooded areas by confining rivers within artificial banks. That means areas outside the levees flood less frequently. It doesn't mean they have zero flood risk at all, since it's always possible to have an extreme event that overwhelms the levees. For earthen structures, overtopping of a levee can cause erosion and even failure or breach of the berm. That can make flooding even worse than it would have been otherwise, especially if people weren't evacuated from the area ahead of time. So even though they're a pretty simple solution to the problem of flooding, levees aren't perfect. Sometimes getting that water out of the channel is exactly what you want, though. Another tried and true flood control technique is diversion canals. These are human-made channels used to divert floodwaters to undeveloped areas where it won't be as damaging. Often it's not possible to widen an existing river because there's already too much development or for environmental reasons. So instead we create a separate channel to divert floodwater around developed areas and back into the natural waterway downstream. In most cases, there will be some kind of structure at the head of the diversion channel to help control which route the water takes. For normal conditions, water will flow through the natural river. But when a flood comes, most of that water will be diverted, reducing the flood risk to developed areas. But it would be nice if all that water didn't make it into the river in the first place. That's only possible with the other major type of flood control infrastructure, dams. These are structures meant to impound or store large volumes of water, creating reservoirs. Dams meant for flood control are kept partially or completely empty so that when a major flood event occurs, all that water can be stored and released slowly over time. The theory here isn't too complicated. We can't change the volume of water that comes from a flood, but with enough storage, we can change the time period over which it gets released into the river. Big sloshes of water into this bucket come out slowly over time. As long as the sloshes are far enough apart and the bucket is big enough, you almost never see significant flooding out on the other side. But not all dams are built specifically for flood control. Many reservoirs are intended to stay as full as possible so the water can be used for hydropower, supplying cities, or irrigation of crops. If a water supply reservoir happens to be empty at the time of a big flood, it will work just like a flood control reservoir, storing the water for later use. But if the reservoir is already full, they have to open the floodgates to let the water through. This can be frustrating for the residents downstream who may have thought they had protection from the dam. In many cases, a dam can serve multiple purposes at the same time. Different zones called pools are established for different uses. One pool is kept full to be used for hydropower or water supply, and one is kept empty to be used for storage in the event of a flood. Finding the right balance point between how much storage to keep full versus empty is a complicated challenge that considers climate, weather, and the maximum amount of flow that can be released without damaging property downstream. Some dams vary the size of these pools over the course of the year, depending on the seasonality of flooding. And some even use risk indicators, like the depth of the snowpack within the watershed, to dynamically adjust the volume available to store a potential flood. I've been using the term flood control throughout this video, but the truth is that term is falling out of favor. Now, if you ask an engineer or a hydrologist, they're more likely to talk about flood risk management. Our ability to quote unquote control Mother Nature is tenuous at best, and the more we try, the more we realize this. Even if expensive infrastructure is helpful in a lot of circumstances, at best it is an incomplete strategy to reduce the impacts of flooding over the long term. For one, flood control structures, especially levees, can protect some areas while exacerbating flooding in other places. For two, overbanking flows are actually beneficial in a lot of ways. Just like wildfires, flooding is a natural phenomenon that has positive effects on the floodplain, like improving habitat, ecology, soils, and groundwater recharge. And for three, we're understanding more and more the true value of resiliency. That is, instead of reducing the probability of flooding, instead reducing the consequences. This is normally accomplished with strategic development, like reserving or converting the floodplain for natural wetlands, parks, trails, and other purposes that aren't as easily damaged by flooding. In fact, flood buyouts, where high-risk property is purchased and converted to green space, is often the most cost-effective way to reduce flood damages in the long term, even if not the most politically popular strategy. It's not likely we'll ever have the ability to reduce the volume of rainfall during major storms. And in fact, many locations are already experiencing more extreme rainfall events than they ever have due to climate change. But we will continue to develop strategies, both structural and non, to reduce the risk to lives and property posed by flooding. If you're here at the end of the video, I'm guessing you spend your valuable free time learning new things about the world. You probably also don't enjoy watching ads like this, which is great because Nebula doesn't have any. Nebula is a streaming service built by and for independent creators like me. Improving access to resources while preserving and replenishing those resources, this is what we do at Veolia. Solid and liquid hazardous waste generated by commercial and industrial activities represents a risk to people and the environment. Contaminated packaging, batteries, paint, clinical waste, hydrocarbons, industrial effluents, and chemical products. We take charge of waste like this every day for disposal or recovery in full compliance with all relevant regulations. And we guarantee the traceability of the entire cycle. How and why? At a glance. Hazardous waste treatment starts at the site where it was produced. Chemical experts analyze its characteristics and recommend the correct solutions for collection, processing, and recovery. A manifest makes it possible to track each of these stages. Waste is packaged and labeled to avoid any risk of cross-contamination. It is then taken to a waste pre-processing facility. Hazardous products from multiple sources are sorted and consolidated. They are then taken to a dedicated waste treatment plant. Waste is identified and analyzed in a laboratory as soon as it arrives on site. The type of treatment is determined according to its precise nature. Processing aims to neutralize pollutants, extract the recoverable fraction from the waste, and valorize the energy potential contained in it. Waste that contains acids, heavy metals, or highly toxic liquids is processed using physiochemical processes. A series of chemical reactions inside a reactor neutralizes the acids and captures contaminants. Valuable fractions are extracted from waste hydrocarbons and solvents by centrifugation and distillation, so they can be regenerated for future reuse. Where water is contaminated with organic pollutants, the solids are separated using dissolved air flotation and evaporative systems. Recovered water is recycled, and biodegradable matter is placed in a bioreactor, where it is digested by microorganisms in a few days. Thermal processing by incineration is used for most solid and liquid hazardous waste that cannot be processed in other ways. The waste is burned in a rotary kiln incinerator at very high temperature. Combustion gas is captured, filtered, and scrubbed. The energy released is then recovered as steam and electricity. Final residue and inert hazardous waste that cannot be recovered is taken to specialized landfill sites. It is stabilized, then landfilled in safety cells, in full compliance with the most stringent environmental standards. By controlling the complete hazardous waste processing cycle, our solutions reduce the environmental impact of industrial activities, avoid the dispersion of pollution into the environment, and promote the circular economy.